Hello to each and everyone. My name is Karan, and this is a example series number 4. Here, the our main goal is to understand the constraint type of, how to apply the constraints, and make sure whenever we say about context, they are simply the subset of constraints. So constraints are something like how two bodies or two surfaces are tied together, or like how they are just constrained so that they have a restricted motion. That's what we will see with an example, and also in this example, we will see some of the plastic behavior of the material, which means nonlinear plasticity. I mean nonlinearity of material we will be seeing. So here we can see the quickly what exactly the question tells us about. So we have to create two surfaces. So it's not only one. So the left side of the surface, like if the one of them is the base surface, another one is a column surface. So the base surface left side is fixed, and the surface of the column horizontal. Okay, so the top surface has given a translation of 100 millimeter and rotation of 90-degree. And we have to define another step. So that's the first step. So in another step, we have to remove the displacement and rotation. And then we have given the dimension of the bottom plate, and then we have okay, so they are welded together. So this column and this base plate are welded, which means we have to use constraint tied nodes, and we have a Young's modulus as well as Poisson's ratio, and we also have the material plasticity. At 400 MPa, the yielding starts, and the ultimate strength is 600 MPa at 0.3. So perfect. So all fine. So we are going to model this particular uh, thing. And so as we know, like we have to start with the part. So we define our first part. Let's say this is the base plate. So it's a 3D part right now. 3D deformable, solid extrusion, all fine. And the dimension given here is like for base 200 by 200 into 10. Okay. So let's define this. Should start from 0, 0. Should go like 200, 200. Perfect. All fine. Then we are done, and we need to define a depth of 10. Perfect. So this part is ready. We have to again click and define the column. Okay. 3D fusion solid all fine, and the dimension is like 10 by 10 into 200 as a depth. Okay, so we define this 0, 0, 10, 10, and the depth is going to be 200. Yeah. All fine. So both of the part are ready, and now we have to define the property. So to define a property, we have to define initially the let's assume this material as steel, and we'll first define the elastic properties. So elastic isotropic is given 200,000 MPa, 0.3 as the Poisson's ratio. For mechanical, we also have to define the plastic properties. So at 400, if I remember, 400 MPa, the yielding starts. Define another row. And when it is like 600 ultimate tensile strength, we have a plastic strength of 0. Perfect. So that's it. Nothing more. We have to mention it here. Let's define the section. So let's define this as okay. As a part, we can define continuing homogeneous. Thickness all okay. Now assign it. Okay, so assign the first the column. Okay, now the big here. Perfect. Okay, so we have done the definition here. Now we have to define the assembly. So here we have to define both of the part dependent or independent. I believe like independent will be the best. And the reason is like when we are meshing it all together, we can independently or dependently mesh on it. So you can define dependent mesh on part or anyone. So it's all up to you. So let's assume any of them. And you can also just make the offset. Right now it is all aligned, so make it offset so that we can understand how to do the translation and put it back to on the plate as per the question. So okay, so let's make it dependent. So okay, we apply. So let's make the translation of this plate from hold on. Yep. Sorry. Yeah, from this point to this point. But before I go, I just want to define two surfaces. It will really help us right now at this point. So because we need to tie a column and the base. So base top surface, column bottom surface, we have to tie. So let's create a surface here. So let's make that like base top. So we define this as one of the surface, and then we again click. We say column bottom. Oops, sorry, column bottom and continue. We define this as here. Okay, now both are defined. Now let's put it all together. We have to go to translation, select the instance. We want this instance to be translated. We say done. So the first point I want to translate is going to be this one here, and the last point should be here, or the end point. Okay, I'll find here. So we have defined the geometry as per the question. So let's check it out question again. So here is the question, and we have to fix this part, and we have to make the rotation as well as translation in the opposite of it. Perfect. So here, make sure to do that, we have to fix this part, and we have to apply rotation and each and everything opposite to the y direction. Okay, opposite to the y. So we will make sure to apply this. Perfect. So assembly is all done. We have to go to the step. So okay, so I have to create two steps. One step I will be applying the load, another step I will be removing the load. So I have like apply load, then I just static journal. We define as nonlinear geometry, and I define it should start at 0.1 at least. Okay, I can increase the increment, or and also can make it like 0.1 as maximum. It doesn't matter. Or yeah, so I define another step where I say remove load, and again static journal. Again nonlinear is on. You can again define it as 0.1 as well as 0.1 and as 1000. Again, I'll find the steps are all defined here. Interaction, yes, it is important. Now we have to define our interaction between our plates. So these are tied all together. So it's a tie constraint one. Let it be constraint one. So now we already know the surface. Hold on, since we have already defined it, so we go to the surface. So master surface is our base top. We continue, and the slave surface is our column bottom. So now you can see how like easily we can just apply it here. Easily we have applied here. So we said all okay. Once you have the circle, it shows like you have constraint contact. Now make sure whenever we have the solid elements, these solid elements are generally only have translation degree of freedom. But as per the question, we have to apply rotational part also. So as to do that, we have to define another constraint Q, that is a rigid body. We make it continue, and it's going to be we have to define a reference point, and then we have to define tie nodes. So let's first define, we go to the tools, reference point, and define it anywhere, doesn't matter, we define it here. All fine. Now the next part is to define the constraint 2, rigid body, perfect. So okay, reference point we have already selected, so easiest one, we select this one. Now we have to do pin node or tie node. I mean, we are defining all the nodes to be as a rigid body so that it can translate as well as it can rotate. So for pin it is only translation, for tie it is both. I select okay, and I select this part, I mean all the nodes, and they all are tied all together. So okay, everything is done here because we have tied it here. Now what we have to do, interactions done, we have to apply the load. So as told earlier, I have to put the initial boundary condition, as the displacement and rotation, displacement boundary condition. So I select this part and I said done. All this u1, u2, u3 are going to be 0, which means it is fixed as per our. If we see again, so here it is fixed, we fix it, and now we have to apply the 100 millimeter of translation as well as 90 degree of this. It's going to be minus of y direction. Okay, so I again go to the loading condition. It's again displacement boundary condition. So it's the apply load. We apply it here, and then we have to do continue. We have to select this reference point. All okay. Now we want u2 is minus 100 and ur2 is going to it's going to be 90 degrees, so we have to put it like radius, so it's like minus 1.57. That's what 90 degree means. So everything is all done, load is applied. Now before, okay, we have to do mesh also. We're going to do part. Okay, so either you can select the by default or we can just define the global seed size. So let's define it as 3 is going to, or let's say 3.33, because I have checked it earlier and I will let you know why I did it. We say mesh, yes. So yeah, this part is defined. Now I have to define column. For column, I just wanted 3, apply, okay, mesh it, yes. Now if you take an assembly, now the reason why I have selected this particular type of mesh size is because like when we have the constraint tied nodes, we have a very small tolerance. So I always want it to be exactly get fitted when we have tie nodes. Unless like there will be a bit of errors or some warnings, so we want to get it out of it. So make sure, try to find it out the best way to fit all together all these nodes. Okay, so that everything is all fine here. Let's define the the element type. So it is 3D stress. So let's check it out. In our case, we have to check it for remote displacement, blah 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 blah. Okay, yeah, so it all finds 3D stress only. The standard, so you can either use reduce integration or not. So yeah, let's use reduce integration. It's all okay, linear, and I guess it's all perfectly fine for both of them. You go to the assembly. Now we have to check it out. We have to run it. That's it. I mean, we are all done with it. But we have to understand one thing, like we have to remove the load also. So let's say I have applied the load. Let's say this was a column. I don't know if you can see it. This was the column. I applied a load. It bent down. Now, since it bent down, I also have to understand that when I have to remove the load, okay, so it is again like it is the first load is already applied here, correct? So what we have to do, we have to remove the first load, correct? The apply load. Once we remove the apply load, then what exactly is going to happen? Then it will try to come back to its original position, or not original position, because it's a plastic. I mean, whatsoever the plasticity is going to have in the material is going to have it, and will return try to get a bit of plasticity. This is what exactly like plasticity nature shows. So yeah, so this is how like plasticity in nature is being shown, like a bit of plastic strain is going to be occur after the release of the apply load. So that's what we have to do. So in the second step, we have to remove the apply load, so that from its own how much we will see it will come back. Okay, so that's why we have to go to the load again. We have to go to the manager, or we can just go from I guess from here, manager, and boundary condition manager, and this is propagated remove load. So this is what we have to remove. Also, we don't want to bring it back, correct? So we don't want to apply any load so that it tries to bring it back, unless it becomes again the not the elastic problem, but you have a plastic, but somehow you just force it back to make it at the original position. But we want the plastic nature. So what we have to do, we have to deactivate this, which means like when we have a remove load, it will be automatically from its own. okay, as per the material properties. So that's it. We are all done, and let's try to submit the job. We can tell that constraint model continue, all okay, fine, and then we can just submit it and then check it out the analysis. It's going to take a bit of time, so we can also monitor in between, like how is everything going. Uh, okay. Also, like I hope like you guys have to understand about the concept of this plasticity of adding two steps. So make sure in steps you can add as many steps. So you can remove the load, you can apply the load. There's a cyclic way of understanding step behavior. So this is really important for us as a broader prospect. For example, let's say when we have like fatigue analysis, or when we have let's say cyclic loading, this is exactly where like we can go ahead and define as many steps. So it's important. So as you can see, it's converging, and for sure, like in these problems, the solution have to converge so as to get a finite answer. And these computational efficiency, I can say, the time dependency totally depends on the hardware availability. So let's say if I have a really good hardware, then I can expect like these simulations are going to work really fast. But unless it's gonna take a lot of time, so it totally depends. That's why we don't sometimes get so much uh, bigger mesh, or sorry, smaller mesh, because it takes a lot of time to compute. So everything has to be taken into account. So yeah, this is what's happening. So the analysis is perfectly fine. So this particular step is, if you can see, it starts with 0.1. I mean the time step. That's what we have defined, correct? I mean, it always try to check it out whether that particular time step works or not. So this is a time step, and soon or later, what's going to happen? Like once it finds like it is going to increase the time step each once it finds the equilibrium condition. Okay, so here I have completed the analysis since it took a bit of time, and I don't want to make the video a bit long. So this is what we have completed. Also make sure like when we have the boundary condition manager and we have to inactivate the applied load. Okay, don't inactivate the fixed boundary condition. Okay, so always try to name them so that it becomes really clear when you are which thing you have to inactivate or activate or propagate internal. Okay, so let's check it out the analysis. So we go to the results, and then we see like the initial case. So from here we can check it out the actual deformation. So as you can see, the initially it starts bending because that's what our translation as well as our rotational loading case was applied, and after some time it will get stopped, and then you will see it will try to return back. See, so when the column tries to return back to a particular position, that's where like the plastic strain till where the elastic region exists, and after that all the deformation is because of the plasticity, the material model that we have defined. So this is what we have done in this particular analysis, and you can also check it from here how it goes on, and from again then it takes a bit of backside. That is all because of the elasticity that exists in the model. So you can also check it out like the equivalent strain, like plastic equivalent strain. This is what exactly we check it out in terms of plasticity. So this is plastic equivalent strain, and it only tells like how much strain a body exhibits. Yeah. So this is peak value, and that's it. So this is going to be the constraint part, and we will do one more example for the contact part, and just let you know that they have a really in detail theory and how exactly the constraints, the contacts work. So I will like to let you know that please try to focus more towards theory so that you can understand how these analyses are going on. And after all, so that you can understand what exactly each and everything, what exactly is the element type. So yeah, that's it. Thank you.